Hey, welcome back. This is the second video in video series 2, and we're going to be covering the ideal gas law. So far we've talked about relationships between certain aspects of a gas, like pressure and volume, or volume and temperature. But is there one unified equation from which we can analyze a gas? Well, this is where Emil Claperyon comes in. And this won't be the last time you see his name in AP Chem, but he was born in 1799, and through some complicated mathematical derivations, he got the ideal gas law. So the ideal gas law says that PV equals nRT, or pressure times volume equals amount times a constant times temperature. And this constant can change depending on what units you use. Typically, we use ATM, liters, moles, and Kelvin. So our R constant is going to be 0.0821. Sometimes you'll see also 0.08206. I mean, it's just depending on how many sig figs are in the problem. But sometimes you also may see 8.314 joules per mole Kelvin. And this is more typical when you're using kilopascals. And you may be wondering why there's only one unit here when we have like ATM liters up here. Well, that's because work is pressure times volume. So work is a form of energy. So therefore we can convert like that pressure times volume into joules when we're using different kinds of units, but we're not really going to use this constant as much in this class. So there you go. And just always remember again to use the right units. And then before we do a practice problem, I just wanted to talk about standard temperature and pressure. So you may see pretty often that in a problem, it'll say that a gas is at STP. So this just means that it's at 0 degrees Celsius and 1 atmosphere. And since 1982, it's actually been 0 degrees Celsius and 1 bar, but 1.013 bars is like basically equal to 1 atmosphere, so they're very close. So usually we just kind of sub in 1 ATM instead. And note that 0 degrees Celsius is 273.15 Kelvin. Okay, let's try a practice problem. I have 2 liters of oxygen gas in a container at STP conditions. How many atoms of oxygen, not oxygens, oxygen are in this container if we can assume that the oxygen gas is following ideal conditions? So that is one thing about the ideal gas law that's important to note, is that it's only going to hold when there are ideal conditions. So it's really useful because if we have PV equals nRT, say we didn't know the temperature, but we knew the pressure, the volume, and the amount, we could find the temperature, right? Just by solving for it using the equation. But it's only going to work when a gas is at these specific ideal conditions, which is going to be discussed in a future video. But so far, just when you're using it, you do have to assume that the gas is under conditions in which it has certain properties that we can apply to the ideal gas law. Okay, so what do we know in this problem? Well, you know the volume, and from STP conditions, we also know the temperature and the pressure. So now we're just solving for the amount in moles. So our pressure is going to be 1.00 ATM times 2.00 liters is going to be equal to our N times our constant 0.0821 liters atmospheres over mole Kelvin. And then finally times our temperature, 273.15 0.15 Kelvin. Okie doke. So now you can just whip out your trusty calculator and do some division. So we'll have 2 divided by 273.15, and then divided by 0.0821. So that's going to give us an n is equal to a large decimal number, but let's remember to round to the amount of sig figs. So we have 5 sig figs in the Kelvin statement, but since everything else only has 3 sig figs, we'll round to 3 sig figs. So we'll just say n is equal to 0.0892 moles. And then from that, we can multiply by Avogadro's number to get the number of oxygen gas molecules. But then we would have to multiply again by 2 because each oxygen gas molecule has 2 oxygen atoms in it. So that's how we would do this problem. I hope that made sense, and I will see you in the next video.